Let us now look at the conservation of energy equation. Recall, for a closed system, our change of energy within our system is equal to our heat supplied less our work done. And this can be evaluated on a per time basis, i.e. as a rate. Our left-hand side of our conservation of energy equation for a closed system can be expressed as follows. Our time rate of change of our total energy of our system is equal to the time rate of change of our total internal energy, du dt, plus the time rate of change of our kinetic energy within our system, plus the time rate of change of our potential energy within our system. Now, when mass is able to cross our control surface, i.e. enter and exit our system becomes open and we have to modify our conservation of energy equation. To do this, we modify our conservation of energy equation to consider energy flow into and out of our system. Now we are going to take this equation at face value. This equation is derived in MEMS 0071, Introduction to Fluid Mechanics, using the Reynolds transport theorem. Now our conservation of energy equation for an open system is expressed as follows. Our time rate of change of the total energy of our system, dE dt, is equal to the rate at which heat is supplied to our system, Q dot, less the rate at which work is done by our system, W dot, plus the sum of our mass flows into our system, carrying an enthalpy, a velocity, and a potential energy, less the sum of our mass flows exiting our system, carrying an enthalpy, a velocity, and a potential energy. So if we look schematically at our system below, we recognize that m dot 1 is entering our system at state 1, and m dot 2 is exiting our system at state 2. Now m dot has properties associated with that state, such as pressure, temperature, specific volume, internal energy, enthalpy, entropy, velocity, as well as elevation. At state 2, our fluid is going to have the same properties. Thus, m dot 1 is able to bring in energy into our system in a form that includes our enthalpy, our kinetic, and our potential energy contributions. And our fluid can also take energy out in the form of enthalpy, kinetic energy, and potential energy. Now, this term, i.e. our energy flux, that is associated with our mass flow rate has three unique terms. Our fluid is able to bring in enthalpy, which is going to be the sum of our internal and pressure energy within our system. Our fluid is also able to bring in a kinetic energy in terms of our velocity squared, and it's able to bring in any potential energy in terms of our gravitational constant times our reference elevation. Our fluid exiting our system is also able to take away energy in the form of enthalpy, kinetic energy, and potential energy. Now, when we evaluate these energy fluxes, we have to be cognizant of our units. So if we work through our conservation of energy equation and look at our units, we have the following. The time rate of change of our total energy of our system has units of kilojoules per second. The rate at which heat is supplied also has kilojoules per second. The rate at which work is done by our system also has units of kilojoules per second. Now, if we look at our energy flux terms on the right-hand side of our conservation of energy equation, we can evaluate what energy is being brought into our system by our mass flow rate. And the first one is enthalpy. So our mass flow rate has units of kilograms per second, and our enthalpy has units of kilojoule per kg. Thus, m dot h has units of kilojoules per second, which is aligned with our change of our total energy, the rate at which heat is supplied, and the rate at which work is done by our system. Now there's two terms that differ. If we look at m dot associated with our velocity squared and m dot associated with our gravitational acceleration times the elevation of our system, and if we recall 1 Newton is equal to a kilogram meter per second squared, we can see m dot times our velocity squared gives us kilogram meter squared per second cubed. And if we recognize a unit is a kilogram meter per second squared, we'd have a Newton meter per second. A Newton meter is a joule, and we're left with joules per second. The same goes for m dot gz. Our mass flow rate is kilograms per second, gravitational acceleration is meters per second squared, and z is meters. Once again, we're left with joules per second. Now, for our conservation of energy equation to obey homogeneity, we have to divide these terms by a factor of 1,000 to get them into kilojoule per second. Otherwise, we are going to have non-agreeing units within our system where our kinetic and potential energies are going to outweigh our energy contribution due to our enthalpy, our work done by the system, and our heat supplied to the system. Now, when we evaluate our conservation of energy equation under steady state, we know that our time rate of change for total energy has to be equal to 0. That means that individual contributions, i.e. our internal kinetic and potential energies, all have to be invariant with respect to time. Thus, if our left-hand side of our conservation of energy equation is equal to 0, we can express it in terms of energy entering and exiting our system. On our left-hand side, we have Q dot, which is heat supplied to our system, plus the sum of I is equal to 1 to n, m dot I, with our respective energy terms. Our left-hand side represents our energy entering. On our right-hand side, we have energy exiting our system, i.e. work done by our system, plus a sum from j is equal to 1 to m of m dot j of our respective energy terms. And we can solve for our respective terms of interest. Now, this is going to be our governing equation for steady state devices, which this will be applied to pumps, compressors, boilers, turbines, condensers, throttles, traps, and calorimeters. Now, each of these devices will have a unique conservation of energy equation describing its behavior. Some devices will produce no work, some devices will have no heat transfer, some devices have no change of velocity or elevation, and we will express this conservation of energy equation accordingly. Now, if our energy changes as a function of time, our conservation of energy has to be expressed in a transient formulation. That is, the properties of our system can evolve as a function of time. And this will reduce to a first-order differential equation. So, oftentimes, our time rate of change of energy is not equal to 0. That means the time rate of change of our total internal energy plus the time rate of change of our kinetic energy plus the time rate of change of our potential energy may be non-zero values. Oftentimes, we are not interested in the time rate of change of our kinetic or potential energies, for we assume these to be negligible, and rather we're focusing on the time rate of change of our total internal energy. And this would be equal to the right-hand side of our conservation of energy equation, as we are familiar with.